So let's look at that stuff. We got some double integrals. Now there's really two ways to do this. One is to do just a regular old integral with nothing really too complicated about it, but let's set up this scenario. So we'd think about maybe a box right here, and we can integrate this on the x from a to b over here, and then we could also integrate over the y's from c to d over here. And the way that we would write that is kind of like this. C to d on the outside, and then we'll put the dy kind of like over here somewhere. And then we'll have the x be on the inside, so it would be a to b, and then there's just a dx right here. So that's it. You know, that's going to be really easy. You're just going to multiply. You can eyeball this, right? Because you can see you're going to be multiplying base times the height, and you'll just get the area. So therefore, the dx dy, I mean, you can literally just call this the area, like dA essentially, this whole component right here. And we'll kind of explore that a little bit more later. But yeah, it's basically the area of this. So length of AB, like the CD. The way you can kind of start evaluating this is do the inner integral first. So you're going to integrate over dx with nothing. It's just going to be x. And you're just going to go from a to b. That would be b minus a, right? Okay, and then so that's your integral there. And then the next step is to just do the other integral over this. Now, we can sort of consider this as constants because it's an x, you're integrating over y. So let's just shift the x's outside of the integral and just do your integral right here over dy. And it's going to be exactly the same thing as there, but just with a y and different letters and stuff. But you're essentially just getting the area like that. The next way to do a double integral is actually in 3D. So let's draw the 3D graph, something like this. And we'll draw a little box right here, kind of still representing a little square area that we're interested in. And we're going from A to B on the x's, and just to label that one as x, and just to label this one as the y, and this one as the z, just so we know what we're doing. And for the y's, we're going from C to D, and that's basically it, right? But we're going to throw in another component into this integral, which is a function. And you could really think of it as the z up here, because a function of x comma y is the same thing as saying the z, right? So I'm going to draw like a little thing here. It will be like a function kind of thing, that, you know, and then we'll connect that to this box, because that's going to be hovering over that box inside of that square. So what you're going to do is essentially, this will help you to find the volume that is contained inside of this box. We could think of this as height, okay? So here's height as a function of x and y. And if you're going to find the volume, then you're going to multiply the area times the height. So we'll set this up like this. We have the outer integral, which is c to d, and then we have the inner integral, which is from a to b, and the function of x, of h, x, and y. And then this is going to be over dx, and then dy on the outside. Let's call this thing x squared y. And so if I was going to do dx, and on this side a to b, and we would continue this doing dy, this side c to d, you'll solve the x integral first. So you'll go x to the third over 3 and go from a to b. And then just like we did before, you're going to pull out the next integral, and you're going to do it over here on this side. And you're going to basically forget about the x's now, because they don't matter anymore. You're integrating over y, so you can pull them all out. You go c to d, and then there's still going to be the y left over from that, which you can integrate over dy, which of course will be y squared, etc., etc. But yeah, so now it's almost as if you've already solved this integral here from dz, turned it into this thing here. Now you solve the dx, and then boom, now you solve the dy. 1, 2, 3 steps. But this is how you do volume. So the key things to remember here are that area is going to be equal to, could be dx dy, or it could be represented as dA. And this is for the rectangular areas, these little squares. And the other thing is to remember that the volume could be represented as dz, dy, dx, or it could be, you could solve the dz integral already and just simply put like a function of h or something, hy, and then you could even represent that as dA over there. So function of h over the area, multiply height times the area, get the volume. Hell yeah. Now let's try reversing these integration limits. So reversing the integration. Let's say I had 1 to x, or 1 to 6 right there, and then I'm just going to throw down a random integral. Doesn't really mean too much. I'll just put it down. We're going to 5x, so we're kind of computing some sort of volume type of thing here. And then we're going to go dy and also dx. So we have the x's on the outside and the y's on the inside. We're going to want to switch those. And one thing that we can be very sure of is that the outer limits are always constant. So if you can make that happen, and you can see that happening, then it's going to be really good, because now we can draw it. And every time that you do a reversal process, make sure to draw it, so that way you can visually see what's going on. We're going to start with the outer ones. So 1 to 6 is where x goes. That's going to be here, 1 to 6. 1 to 6. And so that's something we can just be like absolutely sure of, we know where that's going. And then we're looking at this y's, and guess what? This is actually ln y equals, or ln x equals y. That's an equation you can do here, and this is also the equation y equals 0. So let's draw these two lines. Y equals 0 would be somewhere around here, so we can start at 0. And then this ln of x equals y, let's try to draw that here. So I'm going to do something like that. That's the line of ln of x. And if I wanted to see where the maximum y was, I have to look over here, and I just plug in the 6 there, because that's the maximum I can go. So this will go to ln of 6 right there. So if we want to try to set up the new integration, first let's consider that we're going to want y's on the outside and x's on the inside. And here's just the equation we're looking at right there, dx dy. Now we can start to think about how this is going to look if we're going to integrate from here to there. Then what we're really doing is we're taking lines, and we're just making a bunch of little lines from here to there. But I'm going to draw any old line, which is going to be somewhere in the middle there. It could be a line up here, be really small. It could be a line down here, be really big. I'm just going to draw somewhere in the middle, because now I can see that the x's will start from here and they'll go to there. Now I know where the y's go. I'll just stick those, because they go from 0 to ln of 6. There's really nothing I can do too much further on that. But for the x's, it's a little bit more complicated, because the maximum is 6 right here for sure. But what is this? It starts there. It doesn't really start at 1. It starts on this line somewhere. We just know this is going to be the line x equals e to the y. So that's basically what we're going to put down over here, e to the y. And there we go. We've reversed the integration, and that wasn't too complicated. A couple of other important formulas. Let's look at the average value over an area. You'll be looking at f average is equal to 1 divided by the area times the double integral of some function over that area, dA is So you'll divide the area by the integral of the function over that area. You can also do that with the volume. So f average equals 1 divided by volume. And you would have a triple integral with some function x, y, z, and then with the dv. So those are just more equations to remember. Now let's look at center of mass. We're going to do that in 2 dimensions, center of mass in 2D, and then we're also going to do it in 3 dimensions. So we'll get the x bar is equal to my divided by mass, and you'll get that y bar is equal to mx divided by the mass. So the big capital M's on top are going to be mx equals y, and then you're going to use the surface density xy over that area. For my is going to be x times the surface density over that area. Easy stuff. And for the mass, and this is a 2D mass, in other words, a lamina, you'll do a double integral with no x's or y's there. You'll use the surface density over that area. And then we'll look at 3 dimensions. So very similarly, x equals some m, but here we got yz divided by the mass. Then we got y bar equals mxz divided by the mass, and z bar equals mxy divided by the mass. So for mxy, that's going to be a triple integral, and there's a z, and we're going to use the volume density for that one over the volume. And then we've got mxz being equal to triple integral, there's the y, there's pxyz, and then we have myz being equal to a triple, there's the x, and the pxyz. So relatively easy stuff, and then we'll have the 3D mass being equal to a triple integral of the volume density with no x, y, or z, and dv. And there we go, this is center of mass, not too bad. Now let's try polar coordinates. I've already set up a little graph here, but essentially we're going to kind of do the same thing that we would do here, is we're going to try to integrate some function over this area. And we'll set that up with a double integral, and then here's the function, f of r and some theta, and then we're going to use a dA. And the thing is, dA for the circle is going to be a little different from the dA of a rectangle. So we're going to have to try to convert that. But we should know that if you wanted to find the ds of this line, that would be r d theta, right? And if this little line here, if this little thing had a thickness to it, all right, and I'll make it just a little bigger. But if that thing had a thickness, then we can call that thickness dr. Because that's kind of like the length that it's going in the r direction, very small amount. And then what we can do, if we want to figure out what the area of that length was, we would just multiply. Imagine this was a straight line. It would just be length times width. That would give you the area. So you convert this over here, and you basically say that dA is equal to dr times ds, right? And what's ds? ds is equal to r d theta. So in that case, dA is equal to r dr d theta. So now that's what we would use in this particular situation. And in this case, especially if you're now you're going to need to make some substitutions into your original equations in order to sort of make this happen. So we should probably already know that x equals r cosine theta, y equals r sine theta, and well, x squared plus y squared equals r squared. So by making those substitutions, you should have no problem solving things with polar coordinates. So now I'm going to try to draw out how a triple integral really looks like if we were to draw a little drawing here. It's essentially trying to calculate an area, or sorry, a volume, by using kind of like an elevator. So I'll just put this line in this elevator here, bam. This is that floor, and it's going to go from the bottom all the way to the top. It's the area that you're taking. But back in the day, we were using just lines, and we're taking the line from the bottom to the top. And now we're using an area. We're going from the area. So these are triple integrals. Triple integral. And usually it would say 1, 2, 3, and you would call it like dv. And that would usually be equal to 1, 2, 3. And the dx would be this one. Dx, we'll put that one there. The dy would be this one. It's dy, that one there. And the dz would be, I don't know, the thickness that's there. It's a very, very small thickness. But that's what we put here. Okay, so you kind of have your three components. The area is kind of multiplied at dx dy, so you get the area. And then you're going to push that over the z's. So usually the z's out in the over here are going to have the constant limits, and then you'll have some sort of equations to represent the x and y limits in there. Let's try the surface area integrals. So you would say that the surface area is equal to a double integral of the fx squared plus fy squared plus 1, and then you use a dx and dy. This isn't too bad. You just take the partial of the x and partial of the y and square them, and you can integrate that. But you could also represent this as some kind of a vector. So we'd say the magnitude of dx and then 0 and then fx dx, you would cross that with 0 dy fy dy, and that could also get you the surface area. The key here is to replace z's, any z's that you see, replace them with fxy. So if you do that, you should have no problem figuring out which side the fxy is supposed to go on. That it equals everything else in the equation, and then you start taking your derivatives. Because who knows, the z might be, I don't know, on the wrong side or something. So set it in terms of fxy instead of all the z's. Now let's take this to cylindrical coordinates. This is going to be just a little bit more interesting than the polar coordinates. We'll start with the same things that we had before. X equals r cosine theta, and y equals r sine theta. Z, however, will remain z's. And for dA, there's nothing going to change. We got the r, dr, d theta. But the thing we can do with cylindricals that we can't do with the polars is use the volumes. So this will be r, dr, d theta times dz. And this is kind of representative of what we're doing with adding on these extra integrals. We're just literally just stacking integrals on top of each other. So, and then we're going to go x squared plus y squared equals r squared, as far as that goes. For spherical coordinates, this is where it finally gets really interesting. We'll start with spherical coordinates. And we can draw a 3D plane here. So this is Z, and this is the Y's, and this is the X. And, well, the thing that we'll have here, instead of the radius, is going to be this rho thing. And in order to find it, you're going to walk this way in the X direction, and this way in the Y. You're going to get to that spot. So in order to do that, you got to go some angle this way. That's going to be theta. Get you that, this line to this line. And then in order to get to the Y line, you're going to go from this direction down, and you're going to call that phi. From here down to there. In order to make our replacements with spherical coordinates, let's start by saying that r equals rho sine of phi. So if we do that, then we'll notice that x equals rho sine phi cosine theta. And y equals r sine theta, well, rho sine phi sine theta. And z equals rho cosine of phi. P squared, or rho squared, is going to be equal to x squared plus y squared plus z squared. That's the equation of like a sphere, spherical coordinates. If we're trying to figure out where these thetas would go, well, thetas are going to be pretty simple. They're going to go from 0 all the way to 2 pi. And if we're trying to figure out where the phi's go, the phi's, they only go from 0 to pi. It's going to be basically from the top all the way down to the bottom over there. Okay, and that makes sense because you're going to rotate that to all the way around. Now finally, we'll have the most important components here is knowing how to set up the dv. So dv is going to be equal to rho squared, and then you'll have sine of phi. That's this one. And then you'll go dp, or d rho here, and then you'll go d phi, and then you'll go d theta. So that will help you set up the volume for the spherical coordinates. This is pretty cool. The last thing we're going to try is planar transformations. So let's see if we could do this. It's going to be like an x and a y plane and a u and a v plane. But let's say the x and the y plane had a very weird shape, you know, something like this, and you didn't really like that shape. What you could do is you could say something like, okay, well, if we have some equation of like x and y, you could set x equal to u plus v, and then y equal to u minus v. It's just the example. I don't know what kind of equations you would use, but if you got your x's, y, you can transform them into some other equation. You make up some equation, and now this is going to transform into something like this, where it's like literally a perfect box because you made the perfect equation that made it turn it into a box. I don't know how you'd sort of figure that out, but you'd have to sort of, you know, maybe guess and check and see if you can cancel some stuff out or something like that. Usually these things will be given to you. We'll go ahead and go from like, you know, 0 to 2 and then 0 to 3 there, right? So you can see again that this is going to be the xy plane and this is the uv plane. And you're basically transforming this into that. It makes it look really, really nice in the new box. But in order to do that, because this integral would be really hard, there's like lines everywhere, you'd have to be complicated and stuff. This integral is really easy. You just integrate from 0 to 2 on the u and 0 to 3 on the v. Super easy integral. This integral is really hard. This integral is really easy. But in order to do that, you have to replace this. You'll have to start taking derivatives. You'll set the dx equal du plus dv, right? And you'll take the dy equals du minus dv, because that's what we set up over there. And then this will transform into a little matrix. You could say dx dy is equal to, what are the coefficients here? This is a 1, this is a 1, this is a 1, and that's a negative 1. And so then you can solve the determinant of this little matrix, multiply that by du dv, because du dv is kind of matrix multiplication and stuff right here. But you solve the determinant of this matrix, which would be negative 1 minus 1, so you'd get a negative 2, but it's going to be the absolute value of this, so you'll just get a 2. And so basically, the idea is that the Jacobian, this is called the Jacobian. Jacobian. That's the determinant of this matrix. That's the Jacobian. What the Jacobian is really telling you is, say, on this side you have dx dy, and that's going to be equal to 2 times du dv. Now, isn't that just the area? So what you're saying is that this area is simply twice as big as that area, right? So if we can calculate that, what is 2 times 3? So we see that uv equals 6, and if we go on this side, then if we multiply uv by 2, we should get xy being equal to 12. That's essentially what the Jacobian is saying, is that this area is half as big as that area, or this area is twice as big as that area. So that's interesting. And now you'll be able to replace the dx dy with the 2 du dv like we did in regular old substitutions. This is kind of like a double use of super powerful planar transformations. So I hope you enjoyed this video, and stay tuned for more. It's crazy.